day, students. Today we shall learn about a particular extraordinary phenomenon called superconductivity. Now, metals, they usually show resistance at room temperatures. This is because in metals there are surplus or excess of electrons present in that material, in that lattice, along with the atoms or with the ions of that material. There will be excess number of electrons that can move about that material in that lattice. So they are delocalized. They are not localized to a particular point. They can move around. So we can say that in a pure metal, the atoms exist as a lattice of ions surrounded by a sea of delocalized electrons. Now at room temperature, all these ions, we will be in a thermal equilibrium. And hence, all these ions will experience thermal motion. They'll move about a bit in a very fractional amount. And this thermal motion can scatter the electrons. Now, as the temperature of that metal or material is increased, the ions in it will have a larger thermal motion, and this in turn will cause a larger scattering of electrons. This scattering is the main cause of the electrical resistance. Now in this animated video, we can see as the temperature has increased, the positive ions, they move about a lot more. So initially, when the temperature is low, it is increasing now. Okay, so when the temperature is low, the electrons, red electrons, can move about easily. But as the thermal motion increases due to higher temperature, the electrons cannot flow. That is, the resistance is increased. Now let us study how the resistance of metals varies with temperature. As we change the temperature of that metal, how does its resistance change? So here in this diagram, we can see that for a perfectly pure metal, as the temperature in the x-axis is decreased, as the temperature is decreased, its resistivity, electrical resistivity, it is gradually decreasing at the lower temperatures and attains 0 here, right? Now, if the metal is impure, even though we reduce the temperature of that metal to 0 Kelvin, it will have residual resistivity. This is because of the impurities in that metal. Now, in the case of a superconductor, as the temperature is decreased, when it reaches a particular temperature Tc, it is called the critical temperature or transition temperature. At that point, the electrical resistivity becomes 0, and this means that the electrons in that material can flow with 0 resistance. So at lower temperatures, we understand that the metals have lower resistance. Again, as the temperature is lowered, the thermal motion of the ions is reduced and resistance is also reduced. Hence, metals will all be superconductors at absolute 0 Kelvin, right? Because the ions will not be moving at all. But it is not so. Metals are not perfectly pure and they contain some impurities. Hence, impurity scattering occurs and this creates the residual resistivity. It is independent of temperature. Even though there is no temperature, the impurity scattering takes place and this causes the remaining resistance or resistivity in that material. So Even at lowest possible temperatures, the residual resistivity rho naught exists due to impurity scattering. Now, if the impurities increase in that material, the amount of residual resistivity rho naught will increase. Now, let us see how current conduction takes place in different materials. So, in a conductor, the electrons, the surplus electrons, they can flow easily through that material. Even though they are flowing easily through the material, they can happen to collide with the lattice ions or with each other, and this collision will lead to heat produced in that material. Now, in the case of insulators, there are no surplus of electrons, and hence the electrons are tightly bound and they cannot move about. Hence, there will not be any current in it. Now, in the case of superconductors, there will be excess electrons, and these electrons, they pair together to form Cooper pairs. Since the temperatures are very low, there will not be thermal motion due to the lattice ions, and hence collision is also reduced to a very much great extent. These Cooper pairs of electrons can hence flow without any collision through this material, and they can create current without any heat. So, in the case of a conductor, metal conductor, copper cylinder, we can understand that you can induce current in it. You can flow a current in it. But that current will decay in about 1/1000th fraction of a second, right? This is because Joule heating is taking place, and due to that heat loss, the current produced or passing through it can decay. Now, whereas in a superconducting cylinder, if we produce current in it, since it does not have Joule heating in it, the current does not decay. And that decay is given as less than 0.1 percentage in a year. That is very small. So this current produced can be stored in a superconducting material. Hence it has several applications. So from this we understand superconductors are immune to Joule heating. It does not have any heat loss. So let us understand, or let us try to define what is superconductivity. So in certain materials, when it is cooled below a characteristic critical temperature or transition temperature Tc, the phenomenon of exactly zero electrical resistance and expulsion of magnetic fields is observed. So we observe two main points, that is zero electrical resistance and removal of magnetic fields from it. This phenomenon below the critical temperature Tc in particular metals is called superconductivity. It was first discovered by the Dutch physicist Kamerlijn Oons, and he discovered it in the liquid metal mercury when it is cooled below its critical temperature 4.19 Kelvin. And for this, he was awarded the Nobel Prize in Physics in 1913. So this is how the electrons move through a superconductor. At thermal equilibrium, all the lattice ions are in thermal motion. As the temperature is decreased, lattice ions become rigid and the electrons can flow smoothly through that lattice. While they are moving, we can see certain lattice distortions. Now, this is Kamerlijn Oons, and in this diagram, with this plot, he proved the existence of superconductivity in metals, that is, zero resistance in metals. It was first identified in mercury at 4.19 Kelvin. Now, along these years from 1911 to this current year, there have been discovery of several superconductors. It was not alone in the lower regime. Again, near 293 Kelvin, we have been trying to attain superconductors in these recent years near room temperature. So here is listed a few of the metals and alloys in which we have been able to attain superconductivity. Now this metal iridium and all, molybdenum, they show superconductivity at 0.11 Kelvin, very small temperature. But if it is having any impurities, in particular any magnetic impurities, it will suddenly lose its superconducting nature. Again, there are metals in which there are superconductivity has not been attained at all, like copper, iron, and all. Other metals, aluminium, gallium, tin, mercury, and all have shown superconductivity. Now, palladium may not be a superconductor in its pure state, but a combination of bismuth and palladium is again a superconductor. So there are different types of superconductors. We cannot just classify them into a pure state or into an alloy. There are different composites that form superconductors. In this diagram, we can see that the superconducting transition is studied in the pure and impure states of tin. When tin was cooled to its critical temperature, the impure sample showed a gradual decrease in its resistance, whereas the pure sample showed a sharp change in its resistance. Superconductivity was successfully explained by Bardeen, Cooper, and Schrieffer theory, the BCS theory, in 1957. In this theory, the three scientists, they put forward the existence of Cooper pairs. It is a pair of electrons that is joined together by means of a lattice phonon. In this figure, we can see that one of the electrons, they attract the lattice, the ions in the lattice, and this creates a shift in its position. And the shift creates a positive charge in this locality, and that positive charge will attract the other nearby electron towards that. And hence, by means of this phonon interaction, these two electrons, they appear to be bound with each other, and hence they form a Cooper pair. Let us go through some of the properties of superconductors. Now, the current in a superconductor, they can persist for a very long time. Metals with valency 2 to 8, they exhibit superconductivity. When metals are in their superconducting state, the magnetic field cannot penetrate into the body of superconductors, and this phenomenon is called Meissner effect. A superconductor loses its superconductivity when high current is passed through it. As the current passing through it is increased above a critical value IC, that metal can lose its superconducting nature. Now, a general rule for superconductivity to exist is that the product N raw should be greater than 10 power 6, where N is the number density of valence electrons and rho is the resistivity of that material. Again, the specific heat of the material changes abruptly or sharply at temperatures lower than the critical temperature DC. Now let us go through the effects of magnetic field in a superconductor. Now, in a superconductor at critical temperature Tc, if we apply an external magnetic field upon it, it can lose its superconducting nature and return to the normal state. Now, when the critical temperature is again decreased further less than Tc, again we may be able to achieve superconductivity. So this understanding has been plotted in a graph of critical temperature theta c versus critical magnetic field Hc, and we have obtained this curve. So if the superconductor at critical temperature theta c is applied a magnetic field, it becomes the normal state. Again, if its temperature is decreased, it can become a superconductor. Again, if its external field is increased, it can come to the normal state. Again, if its temperature is decreased, it becomes a superconductor. Again, if the magnetic external field is increased, it can become a normal conductor. Okay, so we can tune the normal and superconducting nature of that material. Now, this plot is called the magnetic phase diagram, and this curve can be represented by the mathematical equation Hc of theta temperature is equal to Hc into 1 minus T by Tc square. Now, when the material makes the transition from the normal to superconducting state, that when it becomes the superconductor, it actively excludes magnetic fields from within it. This is called Meissner effect. Now assume that this is a superconductor. Okay. Now it is at room temperature. If we place a magnet above it, it will sit comfortably on it. Now let us pour liquid nitrogen into that sample, into this region. Liquid nitrogen is very cold. It reduces the temperature here. Now, if the material becomes nearer to its critical temperature, Tc, at that point, this material changes into the superconducting state. Now, when this is a superconductor, it will not allow any magnetic field lines to pass through it. So, the magnet that was sitting on it, the field lines that is emerging from the north pole, it has to come back to the south pole, right? Since that field lines cannot pass through this superconductor, it will push the magnet upwards so that the field lines can close like this. And this appears to be seen as the magnet to levitate, to float on top of that material. This is called Meissner effect. And inside the superconductor, the magnetic field will be 0. This figure elaborates it. So at temperatures greater than critical temperature, the superconductor will allow the magnetic field lines to pass through it. Whereas at temperatures less than or equal to the critical temperature, the superconductor will not allow field lines to pass through it. In this figure, we can see that the material is in the superconducting state and it does not allow the magnet to rest upon it. The field lines from the top is supposed to close back into the magnet, and hence it causes the magnet to be suspended in air. So this is explained here. In a normal situation with a ceramic disc magnet, the magnetic field lines, they leave the north pole and enter the south pole. When it is sitting on the surface of a superconducting material above the critical temperatures, at room temperatures and all, so the field lines, they can pass through this material and then close the loop. But if this material is the superconducting material, that is the temperature is below critical temperature, then this material becomes a superconductor. The field lines can only reach up to this point. It cannot pass into the superconductor. So it makes itself float so that it moves up so that the field lines can enter back into the south pole. That is all for today's session. Thank you, dear students.